So we need to talk about a very important concept of a sampling distribution. At least that's in mainstream ways of thinking about statistical inference. The sampling distribution plays a major role, and it's in general just useful for kind of thinking through what we're doing and how we're characterizing uncertainty of our estimates. So first things first, what is a sampling distribution? We're using this term distribution a lot, and there's similarity in all of our uses. So think about what a probability distribution conveys. What are the two pieces of information? It makes it sound simple, but it can involve a lot of information. But what are the two things that you know when you know a probability distribution? You know all the possible values that a random variable of interest may take on, whatever it is that you're studying, and the probabilities associated with virtually any given set of those possible values they might take. So that is, you're able to, it doesn't mean you have a list of them, doesn't mean you have the answers at your fingertips. It means you have the means, maybe through an R function, through a formula, in some cases, a discrete random variable with a small number of possible outcomes. Maybe you have a table. Or you have an approximate table for a continuous one, like used to be popular for normal distributions. So you have answers to the questions of the form, what is the probability that X is an element of, and then any set that's, all X such that some named criteria hold. So that is to say, the questions like, hey, what's the probability that X is less than 10? What's the probability that X is greater than 30? What's the probability that X is between 10 and 30, and so on. So a sampling distribution is just a form of a probability distribution, but it's pertaining to a particular kind of random variable that is of interest to us, and that is a statistic. A statistic is a form of random variable. It's composed of you're doing something to a set of observations in your data, right? You're often start with a simple case of a sample mean. You have a bunch of observations of X in your data, and you take the average of them. That itself, since each of those individual realizations of the random variable has randomness associated with it, or in your perception of uncertainty about where those values may lie, yeah. Then anything you do with those, adding them together and dividing by n, or multiplying them together, or subtracting a bunch and then dividing, whatever you want to do with them, the results will themselves have some distribution, right? They'll have some probability of being in any set we might choose to name. Okay, but what is a statistic? I alluded to it there. It's important to keep in mind when we're talking about a statistic in statistical inference, we're just talking about a function of observed data, right? A function, we're taking the data and doing something with it. I just described a couple of things you can do with it, like taking the mean, multiplying them together. When we do regression, we're going to be taking data, a bunch of x's and some y, some outcome, and we're going to be doing something with them to make estimates of parameters in a regression model. So we will be taking a function of observed data. So I mentioned examples. Common ones are things like p hat. When you see those hats on top, like that little caret on top, that just means it's an estimator. It's being used. It's a statistic that's estimating some parameter of interest, which is underneath. So if p is a probability or a proportion in a population, p hat is some function of your data, like the proportion within a data that's being used as an estimate of the true p probability or proportion. X bar, the second one, a sample mean. S sub x, I'm using a subscript as the standard deviation of, or sample standard deviation of x. How spread out, how dispersed are they? A difference in two sample means, that itself is a statistic that's going to have a distribution. And beta hat, let's say in a simple regression, which we'll see soon, the slope of that regression line. If we think of the underlying model and data that can be produced by whatever processes are truly generating the data, we are estimating a slope with those data. And if we had a different sample, or if the data were generated by the process in a slightly different way, then we might get a different beta. So we're estimating, in some sense, a kind of a fictional but useful quantity in that case. So since we think of data as, or it can be useful, this kind of modeling of what's going on as data being generated from a probability distribution, then any quantity that are computed from their values will have a distribution. So that's why statistics themselves have probability distributions. But because statistics take an important role, not surprisingly, in statistical inference, we have a special name for those distributions. We call them sampling distributions. So sampling distribution on its own doesn't really tell you what you're precisely talking about. It's always sampling distribution of something, sampling distribution of a mean, sample mean, sampling distribution of a difference in mean, sampling distribution of a proportion, and so on. It's always of some statistic. And why we're kind of going through this mental exercise and always sort of keeping what we're about to do in the back of our minds in some way or another is because it's helpful in thinking about how statistic could vary across different samples. Why? Because it's going to help us characterize our uncertainty. When we get one statistic, we want to have a sense of, okay, well, if I want to think about how well that's estimating the target of inference, I want to think about not just this particular value, but how easily it could have been with a different sample other values, so that I can kind of put some cap on how far away from the target of interest it lies. So yeah, again, we're typically just going to have one sample. So why imagine hypothetical samples we could have gotten? Actually, in you're reading for a quantitative book club, if you're reading Bernoulli's fallacy, there's some writing. There's some statisticians and probabilists who don't find this especially helpful and have problems with this. But as I said, it's kind of a sort of mainstream or orthodox way of developing these ideas, although not necessary. So why imagine we're have this concrete problem of estimating from a sample we have? Why does it help to think about these, in fact, infinitely many hypothetical samples we could have gotten? You may find it more or less useful, but let's get to why it could be useful. Well, we want to measure uncertainty, again, and how well the estimate we do have reflects the model parameter it's estimating. So it's not enough to say, for example, x bar, the sample mean, is approximately equal to the expected value of x, the true mean or the process mean. It's not enough to just simply say, hey, my estimated slope that I'm getting from R is, it's approximately the true slope if the model that I'm estimating were really the generating process, which it's not exactly anyway. It's a couple of steps removed. So we need a way to think about how close these statistics are likely to be to their targets, and thinking about a distribution is helpful. Think about a process of you're drawing a random sample of observations from the population of interest and observe, or more often in social science, observing the unfolding of some data generating process that's characterized by a model with some specific parameters, that use some important numbers that give you all the information about that process. So make it a concrete example. Suppose we're measuring, this has been quite relevant recently with a lot of wildfires. Imagine you're sent to estimate air quality index. You want the mean AQI in a region after a fire, and you collect a random sample of 20 observed regions from the region, readings rather from the region. So you've got X1, X2, X so on to X20, and you're just going to calculate the sample mean as an approximation to mu being sort of generic stand-in for the expected value of x. In general, we'll see this notation of x bar with n as a subscript here, x bar 20, to remind us of this isn't just any sample mean. This is a sample mean taken from 20 observations. That's important because, well, our intuition should be and would be correct that the bigger the sample, the better the approximation. And so we we care whether it's x bar from 2 or x bar from 1,000. Yeah. So thought experiment. So each observation, x1, x2, and so on, is an independent realization. If I'm set up to take a random sample, what I find in one place isn't going to make me choose my next place contingent on that, right? If I have a sort of sampling plan of where to go, then I'm getting, I'm drawing from the same distribution of AQIs that exist in this region. So any function such as a mean is also a random variable. So we want to think about the probability distribution of the sample mean from what we get when we calculate these 20 random observations, right? So we think about the fact that the 20 we happen to get could have been a different 20, right? But there are some, it can't be any 20 numbers. It's not going to be -7. That's not possible in distribution. These are numbers that are going to be between 0 and 500. It's not going to be 510. That's outside the range. But if let's say there's a mean of, as in this example, we'll have 160. If there's a really narrow distribution, it's going to also be very unlikely or virtually impossible to get certain sample means that are outside some bounds. So thinking about this probability distribution of x bar 20 in this specific case is we're thinking about a sampling distribution of the statistic. What sorts of values would be more or less probable as a result of this process of going out and collecting 20 observations? Okay, so let's get even more concrete. You're the researcher. You're going out and collecting, I put in quotes because we're going to simulate this, a random sample of 20 observed readings, x1, x2, all the way to x20, 20 observations randomly drawn from around this region. And this matters, or these measurements are meaningful. We have a sort of ordered typology that tells you based on the readings whether they're good or moderate, unhealthy, so on. And so you're going to be using this as a gauge on how concerned we should be, maybe even whether we have a warning about people staying inside or putting on air purifiers. So unknown to you, so now behind the scenes, if you could be omniscient and know all, you would know that the distribution of X, not the sampling distribution, the underlying distribution of the phenomenon you're studying, these AQIs, has a normal distribution with mean or expected value 160 and a standard deviation of 25. That is the square root of the variance of X is 25. So 160, it's, using this chart, it's just about, it's in the unhealthy range, right? It's from 151 to 200. Okay. So let's ask, what is the probability that your estimate is more than 10 away from the true mean AQI of 160, right? When you take these 20 and take the sample mean, how plausible is it that you might be off by more than 50? These are kinds of questions you want to be able to answer. You want to know the sampling distribution because you want to know how much confidence to put in your estimate. How confident are you, for example, that it truly is unhealthy on average if you are using that typology. So what do you think intuitively the mean of the sampling distribution of x bar 20 is, and what do you think the standard deviation is? What is it? How's it going to be related to the underlying distribution of x? Right? It gets a little dicey talking about this because we're asking about the mean of a sampling distribution of a statistic that here is in fact itself a sample mean of the 20 observations you're getting, right? So the idea here is if you go out and collect 20 and calculate the sample mean, and I go out and collect 20 observations from the same area in the same way, I'm going to get a different 20, a different sample mean. Someone else is going to do that. If lots and lots of people each went out and got a sample of 20 and calculated their sample means, what on average are we getting, right? Some are going to be bigger than 160, some are going to be less. What on average are we getting? And so it turns out, and I will show you in another video, that the mean and standard deviation of the sampling distribution can be established with math. It's good to know, even if you're not going through the process in detail, what sorts of things we know, just because the math works out and it's deductive and there's not a lot of controversy, and what sorts of things are statistical theory where there's different points of view on, or measurement, what sorts of measurements are better. So this stuff is simple algebra will get us that the expected value, that is the mean of the sampling distribution of your sample means for any sample size n, right? Lots of people each going out and collecting a sample of size n, each of them taking the average, and then us, if we looked at a histogram of those and said, hey, where is the mean of all of those sample means? It winds up equal to the mean of the distribution itself, the underlying distribution of x. Right, and I should mention here, and we'll this works no matter what the underlying distribution is. It doesn't have to be normal. In fact, it can be very weird. In fact, if you had a distribution for x that looked like this, for example, and let's say the sample mean was here, we're going to find out that the sampling distribution may look something like this. It might have a very different shape, but the mean of that sampling distribution of x bar, whatever n is going to be in the same place, right? So lots of people going out and getting different samples and calculating their means. Some will be far away from the truth, some will be close to the truth, but all those hypothetical samples, their means on average will be equal to the mean of the underlying distribution. Right? That's a helpful thing to be aware of. And the variance of x bar is not going to be equal to the variance of x, but it's going to be equal to the variance of x sigma squared divided by n. So that is to say, the bigger your sample size, the narrower the sampling distribution, and the more precise your estimates are. And we're going to be able to talk concretely about those so that we can have confidence intervals around them and so on. Right, standard deviation is defined in terms of variance. It's the square root. So the standard deviation of the sample mean for sample size n is going to be equal to the standard deviation of this is standard deviation of the sampling distribution of x bar, right? Whereas when we just see x by itself, it's implicit that it's talking about the basic distribution here. We could have written sigma squared x here to be more concrete. This is sigma x bar, standard deviation of the sampling distribution, and that's the square root of the variance of x bar, and so commonly written as this, the standard deviation of x, the underlying distribution, divided by square root of n, right, square root of the sample size. So that stuff is just math. The overall shape of the distribution, though, can be established with statistical theory, and that is a lot more complicated, and is proofs of it at sort of different levels of understanding include different levels of difficulty and conceptually. But the bottom line is that the overall distribution, if x is truly normal, the sampling distribution will also be normal. I left out something here, the sampling distribution of x bar, right? And this is also going to be true of lots of statistics that involve adding a bunch of data observations together. But we'll start with this one. The sampling distribution of your sample mean will be normal, but it's unlikely that x itself is normal, right? So it's helpful to also know that no matter what the distribution of x is, right, it's the sampling distribution of the sample mean x bar will be approximately normal. and it'll look closer to normal and behave closer to a normal distribution, a bell-shaped kind of curve, as sample size of n gets larger, and the more symmetrical and the more close to a bell-shaped distribution is. So in fact, even if it's symmetrical but not bell-shaped, that the distribution of sample means will look a little more normal, typically, if n isn't too small, than something that's wildly skewed to one side. And but again, the more normal the underlying distribution, the better approximation a normal is for the standard for the sampling distribution. But as n gets large, it doesn't matter how weird within reason these underlying distributions are. You will still have an approximately normal sampling distribution. And this is one of the primary reasons that a normal distribution is so useful. It's not that the underlying variables tend to be normal, it's that sampling distributions often are, or are functions of normal distributions. And this stuff together in a mathematical statistics class, maybe we'll encounter this name again, referred to as the central limit theorem, at least in a kind of informal way of stating it. So let's actually run some simulations to build up our confidence in this result and understanding of what it is and what its implications are for us in doing statistical inference. So I'm going to ask you to do this, try to do this in R, and then in the next video I'll go through results. Randomly sample 20 observations from, okay, I don't want to, what I'm really meant to do here is not doing this yet. I'm just sampling 20 observations of X. So I'm going around, you're going around and collecting those AQIs, those readings, and unbeknownst to us, those readings, as we draw them, we're drawing them really from a normal distribution centered on mean 160 with standard deviation of 20. So we're going to randomly sample 20 of those, x1, x2, x3 through x20, right? Not that we're not sampling the sample mean. My apologies there. We're going to repeat that several times to get a feel for how variable they are, right? Like maybe you get a 162 the first time as your sample mean, and then you get a 165, and then you get a 157. Notice each time how far away from 160 they tend to be, and what are some numbers that are further away, and what numbers do you tend to get more often, and so on. So do that just using R norm with one at a time, a few times, and then do a bunch at once. So collect 10,000 such samples, calculating and saving the sample mean of each, right? So this is simulating the process, which would never happen in real life, of 10,000 different researchers all going out and following some random sampling procedure, choosing 20 observations, getting their 20 AQIs, each one taking their average and bringing it back to the home office, and then you're the home office. You take those 10,000 samples and you plot a histogram of them to see basically an estimate of the sampling distribution. It's not exactly the sampling distribution because it's still 10,000. It's not infinitely many. It's not giving the true probability distribution of sample means, but it's giving us a close idea. This is very meta, this part, right? This is not something that we're doing in practice. This is helping us think through, the idea is if we know something about the sampling distribution, the hypothetical sampling distribution around the thing we're trying to estimate here, mu, then, when we take our one sample and we get our X bar, we won't know. This is going to be hidden, right? We're taking our one, but we're imagining that we're drawing it from some sampling distribution, and we get our observation, and we don't know if we're over here or over here, but we can know something about how probable it is that we're likely to be a certain distance away from our target, wherever that target might be, right? And that's going to be the reason this is going to be useful. So all right, those are the steps. 1, 2, 3, 1, apparently. 1, 2, 3, 4. And do try that on your own. Maybe pause this to remember what steps I'm asking you to do, and then come back and I'll work through it as well.